Good. I think we're ready. Let's go. So, thanks everyone for coming, for getting up. It's a great pleasure to be here tonight, or it's tonight this morning. It's more or less the same. It's my first keynote ever at an industry conference, so it's a great honor to be here. And I am going to talk to you about something that I think we undervalue a little bit in our community and in our coding patterns. It's how great Scala is actually at unifying three programming paradigms. Usually we talk about functional programming and object orientation. I will add imperative to the lot. So Scala actually mixes those three paradigms, and it's not just like throwing them together, it's actually fusing them together and actually making something out of it. And I don't think we exploit this nearly as much as we should. Because after all, if we're doing Scala, it's not to write better Java, and it's not to write worse Haskell. Scala is its own thing. It has its own advantages, powers, and today I'm going to hopefully show you a little bit how you can actually leverage all of it. And so this is why the talk is titled Functional Object-Oriented Imperative Scala. It's the whole thing. And I will just say one more thing, which is that except for the first intro example, which is completely made up and stupid, after that, all the code examples that I will show are not made up. I took them from my code base. It's actually the scala.js linker, which is basically an application. Like it takes inputs, messages them, and produces an output. So this is typical application style code. And this is my code base for every day. And I literally picked up code from the code base, and I will show you how they illustrate everything I want to talk to you about today. So this is my real coding style for everyday writing of Scala, right? Okay. So just a quick show of hands, who here has less than 3 months experience with Scala? That's 1, 2. Okay, so it would probably be a little bit quick on the beginning of the thing. At the back, can you read this comfortably? Not really. Does this work better? Good. Okay, so this is probably the most terrible Scala code one can write. This is a method that takes a list of ints, returns a list of ints, that it's supposed to double every element, right? And it does that by first creating a variable which will hold the result, initialize it with an empty list. Then it uses a while loop to go over the list, and every time it appends at the end of the resulting list the excess of I. Something is, I don't know. I hope it doesn't bother you guys too much, the echo. So it takes the excess of I, multiplies it by 2, and appends it to the result. So this is terrible because it's not really idiomatic Scala, but worse, it's terrible because it's absolutely inefficient. There are 3 operations that are done on every iteration of the loop, but there are O of n in the size of the loop. There is excess.length, there is excess of I, and then there is append to the result. So in idiomatic Scala, we will get there one step at a time. So what we do is first we use at least a for comprehension for the I. That's still imperative for comprehension. It's for each over a range. Okay, easy enough. Still terrible. Then we can at least use a list builder, because in that way the plus equal is constant time, and then at the final, for the result, which is called builder result, as constant time as well. At least we've removed some of the inefficiency. Then, I mean, we could just iterate over the list itself instead of iterating over the indices and then accessing the elements. So this is the first version that's not terrible from a performance point of view, right? This is, the whole method now is O of n. But yeah, I mean, nobody would write that, right? We would just write this, okay? So in idiomatic Scala, of course, this is a very simple operation to do. You just use map or a for yield, which are completely equivalent, right? Okay, that was the boring part. But I just got rid of a builder and told you it was not idiomatic Scala, but sometimes a builder is actually the right thing to use. Let's take an example. So this is a method from path class path, which takes a sequence of directories and jar files and will build up the IR containers. So the IR is this intermediate representation that Scala.js uses, so in the linker, so it's a business model data structure, if you want, and a sequence of actual files that that were the source of this thing, because the class path can contain jars, but also directories. And if we have directories, we want to expand them to all the files inside the directory. Okay, so this method here has a few things. At the beginning, we create two builders, one for the resulting containers and one for the resulting paths. And somewhere in the middle, in the second if here, we add one element in each of those sequences. So if it were only for that, I would recommend not to use a builder. I would recommend to use a for yield, return tuples of the elements, and at the end, just unzip the list of tuples, right? To get the tuple of lists. But if we have a directory, then we need to walk all the files inside the directory, and in the middle, in that lambda there, which will be called several times, for every path I need to add something to the containers in the paths. And here it's just so much easier. The alternative would be for walk IR to return the list of containers in paths. That would be purely functional. And then I would do a flat map instead of map. So the big for here would have to become a flat map to flatten out the list coming from here. But then, in this case, I basically need to create an artificial list of one element so that it's correctly flat mapped across the thing. In the end, I very much believe that the implementation with the builders is actually much easier to understand. Because if I have a directory, for each file inside the directory, I will have a result. And if I have a jar, the jar is a result. And at the end, I just return all my results. So, but wait, Scala is supposed to be a functional language, right? We were supposed not to use this kind of stuff, not to use mutable states. The thing is that inside this method, I use mutable states. I use builders, which are fundamentally mutable data structures. But if you look at the method from path class path as a whole, it is basically functional. It takes inputs, and for those inputs, it will always return the same outputs. So some of you are going to like take their tomatoes right now and send them to me, because that's not even true, right? Like later on, the file system could have changed. That means that its directory is going to return a different thing. Walk IR is going to walk a different IR, a different set of files. So this is absolutely not purely functional. And yet, in the context of my application, this is purely functional. Why? Because in the context of my application, during the beginning of my entire run and the end of this entire run, the file system doesn't change. So it's in one state at the beginning, it's still at the same state at the end. So from the point of view of my application, this is actually purely functional, because the file system is an immutable data storage. Okay, now you can take the tomatoes. Okay, we've seen builders, which are mutable data structures. We also have vars, which are mutable local variables. So let's look at this other example, which generates appropriate type tests as a JavaScript AST to determine whether a particular expression or value is of a certain type. And the way we construct this is we have this test variable, which is an AST of a JS expression, which will return a Boolean. I initialize it with some generic code that works for basically most classes. And then there are a few special cases. If I'm an ancestor of string, then I also need to try and test if the value is just a primitive JavaScript string. So for example, if you test is instance of car sequence is a super trait of Java long string. And so primitive JS strings are supposed to answer true to are you a car sequence. So here I use a local variable because it's so much easier. And you can see again that it has to do with the ifs and several nestings of ifs. Earlier it was about the ifs, and then inside there was a lambda, the walk IR thing. Here it's a nested if inside. If I have to write this in an without the vars, let's say, so with just vals, this is what it looks like. First, it's longer. Second, I would argue it's easier to make mistakes, because I have different variables. I have test 0 and then test 1, and I use test 0 to build test 1, and then I have this test 2, which is like lexically after test 3, because to compute test 3 I need test 2, and then I have the inside if and all of that. So I will argue that this version is worse than this version with the mutable variables. Even better, I would argue that this is purely functional. So here we have local variables. It's mutable states, right? And yet, I claim that this code is purely functional. Why is that? Well, the reason is, given the set of inputs, it always returns the same set of outputs. And even from a compiler point of view, from a language point of view, this has to be true, because those variables, they only look at immutable data that come as inputs. You message them, and you return an immutable data, which is again an immutable AST for a JavaScript code. And it doesn't matter that in the middle I used a local var, because given the same set of inputs, even if I have vars, there is only one possible outcome, right? So as long as your local variables are not captured in a lambda or in an inner class or something like this, Your method, if it takes immutable data as input and immutable data as output, it's still purely functional. So far we've seen things that are just inside a method. So we have only seen examples where we have a def, it takes immutable data as input, returns immutable data as output, and inside it uses immutable state if that's more readable. This is something, a design pattern, let's say, that I use like all the time. Of course, for a lot of functions, I will write them in what is traditionally considered as purely functional, like just vals, immutable data structures inside. But if I think that this particular method is easier to write and to read using local state, I will use it. But the important part is the method itself, from the outside, it's still purely functional, so that you can compose things. Composition is the one big thing that functional programming gives you. Right? We can go a step further, and we can cross the boundaries of methods with mutable data. Here I have two examples, which are not going to show in their entirety. It's the analyzer of the scala-JS linker. So that's the thing that computes the reachable part of your program. So you might be aware of a particular type of optimization, which we call dead code elimination, interprocedural dead code elimination. The way it works is it starts from the main method of your program, and it computes all the other methods that can be called from there, all the classes that can be instantiated. It resolves all the possible virtual dispatch, and then it marks all those things as reachable, and at the end it throws everything else away. That you can do if you have a whole world view of the program, of course. And to do that, well, it's basically a typical graph algorithm. Like you follow the edges, you switch booleans from false to true, and then you keep following the edges. It's kind of simple. It's also kind of tricky in the details of the algorithm, but basically it's a typical graph following algorithm. And this is something that is actually quite annoying to write in purely functional style. I think probably most functional programmers will agree with me when I say that graph algorithms are a pain in purely functional styles. So here we have a complex algorithm that has many methods, and they share the mutable states in between. So now we've crossed a different kind of barrier, right? Now we've actually we're sharing mutable states between methods. That's qualitatively different from what we did before. But the reachability analysis algorithm as a whole is still a function. It's still purely functional. It takes as input a program and outputs an analysis that says this method is reachable, this method isn't reachable, right? So it's a big file. It's something like 500 lines of code or more by now. It has basically one major entry point, which is compute analysis. I think it's literally called compute analysis in the code. And it takes as input an immutable data structure representing the program and returns an immutable data structure that is the analysis. But inside it has classes with mutable fields, with methods that share those mutable things, set things somewhere, mutate all that stuff, compute a result, and at the end returns the result. So here, what's changed is that it's not just inside the method, it's a lot of methods that share their immutable state. But still, from the outside, from the rest of the program, this analyzer is still one purely functional method that takes a program as input and returns an analysis as output. So while I develop the analyzer itself, I need to be careful about all the mutability that happens there. But when I'm in another file of my code base and I call into the analyzer, I can reason about it as a purely functional function. And it has to be like that. I don't have to even like prove that it's true. Just looking at the interface, I know it's true because it only takes immutable data as input and returns immutable data as output. I don't have to prove that or to reason about the fact that the analyzer is purely functional. I know that. It's a given. Inside, it's tricky. But from the outside point of view, it's purely functional. Great. So, again, I can compose this thing further with the rest of the linker, right? Okay, that was the easy part. Now we move into a different category, which is we work at the instance level. Instance as in an instance of a class. So let's look at this very small interface, or class, which is called the emitter. The emitter is a thing that takes the scala-italy and emits the corresponding JavaScript code. And it has basically one method, which takes a linking unit, that's the program, like the entire program as IR. It takes a builder to output the textual JS code, that is the output, and it takes a logger for logging purposes. And again, it's like earlier, you would say this is not functional. It has a builder as a parameter and is going to write out to the builder. Well, again, in the context of my application, only this method writes to that file. And then from that point on, that file is used as immutable input from the rest of things. So it's as if I had produced an immutable source code that I then use, except I wrote it to a file, and then I'm going to use the file. But again, like from an architectural point of view, this is purely functional. Okay. So inside that thing, things are not functional at all. It's even worse than what we've seen before, because the class emitter is public, and the rest of the program can hold an instance of that class. And it can call the emitAll method, but the instance has mutable state in its fields. So the instance is definitely not purely functional, right? Because if you call emitAll twice, even with the same input, who knows how the state of the instance has changed in the meantime, right? So for example, we have this class caches thing, which is used for incremental compilation. So it caches the results that we computed from a previous call to emitAll, so that if part of the input is the same as last time, we can reuse that portion, the results that we computed, okay? And so, of course, we have the traditional cache method, which is get or else update here below that we use for that, right? And we also have a mutable field, which is aptly called state, in case that was not obvious that it's mutable state. And it starts out as an empty state, but in the emitAll method, it will actually put a new state in that state. And again, this is used for incremental compilation, right? So things that we've computed during one run, we are going to store them in this state so that maybe we can reuse them the next time. For example, one thing that is stored in the state is the core.js lib. And you can see here that, yeah, so it's something that we store in this state that we're going to reuse from one time to the next, because calling here core.js lib.build is an expensive operation, so we'd like to avoid doing it every time if the input of that function hasn't changed, right? So here it's getting really tricky, because from an architectural point of view, I want emit_all to behave functionally. If I give it a given program, I want it to always return the same resulting JS file, right? With the same content. But now I don't have any help from the compiler or the language to guarantee this, because I could very well write emit_all in a way that every time it changes the state, it increments a variable somewhere, and it uses that variable to be in the output of the JS file. So every time I call emit_all, I receive a different JS file, even if the unit, the input was exactly the same. Nevertheless, it's supposed to be functional. So this method here, from an architectural point of view, from the rest of the program, I want to be able to reason about it as if it were functional. I only use mutable state inside the instance of emitter for incremental compilation purposes, so as caches, basically, right? I don't have any tool, any language level support to prove to me that this is true. So when I write emitter, I need to be even more careful than it was for the analyzer, because now I can actually make it wrong, make it behave in a way that it would behave differently on every call, right? So, and yet, assuming I don't mess up in this specific class, then from the outside, I can reason about it as if it were purely functional. And this is what I actually do. When I reason about my program, I reason about it as I assume this method is really purely functional. If it ends up not being true, then the fault is in there. It's not in the rest of the program, right? So I'll just recap a little bit this concept here. The object, the class, from a contract perspective, is immutable functional. But then inside, I use mutable state, which is not observable from the outside, or at least is not supposed to be observable from the outside. So assuming I don't introduce a bug, it's not observable from the outside. And so, of course, like it's already on the slide, but this is encapsulation, right? Within an object, within a class, I have implementation details, which use states. But from the outside, this state, those variables, are not observable. This is the very definition of encapsulation, and this is a very strong, like, I would argue it's the property, the advantage that object orientation gives you. So we've seen composition with the functional APIs, and we see encapsulation with the object-oriented part of Scala, and all in the middle of that, we've sprinkled mutable state and imperative things. Another thing I'd like to say about this specific example here, where I have a class whose public contract is purely functional, but inside I use mutable data structures as caches to incrementally compile. This you cannot write in a purely functional language. I will repeat this. This you cannot write in a purely functional programming language. People will say, but of course you can. You just have to put it in a monad, and the monad will keep the state hidden. But then the caller of that API needs to thread this monad everywhere. So you have changed your public API in order to support private implementation details. Okay, who would like to stand up now and tell me that this is good? It's dark, but it doesn't seem like everyone is standing up. Yes! So here you have a unique power of Scala, of using the encapsulation of object orientation and the mutable aspects of imperative programming to support a better API for your functional component. Can you believe this? Like, this is awesome. Like, this is really, I will say, like the nature of the combination of those three paradigms. And this is something that I use all the time. Like, the entire Scala.js linker is components like this that are really components in the sense that you can actually compose them, because from the outside, they're always purely functional. But inside, they use caches and mutable stuff for incremental compilation to manipulate smaller components, which in turn are purely functional from the outside, which is why you can cache them, by the way, because you cannot cache things that could change, right? Independently of their inputs. Right? A cache is really only a cache if, for the same inputs, it gives the same outputs. So it's really important that this hierarchy of things, every time you have components that are purely functional from the outside, mutable in the middle, and that call purely functional smaller components in the middle. And your entire architecture is made of a tree of such components. Yeah, I just said that. So we use this like as a tree. We've seen the emitter, but it's everywhere like that. I'll conclude with a few smaller details. So open class hierarchies. So far, we've only seen like final classes, basically. But of course, in object orientation and Scala at least gives you open classes. So traces that are not sealed and classes that are not final. So this is new. So far, we've only seen sealed traits and final classes. One example is the linker backend thing of Scala.js. So this is a component that sits around the emitter and abstracts away a few things. But the linker backend itself is an abstract class. It has a contract of methods. Here, I simplified the documentation comments, but this is probably where you actually want to write the most comments in the contract of open classes and traits. Because for open classes and traits, the contract is everything. Right? The signature is really not enough. The contract is everything. And we have one implementation, which is called a basic linker backend. That one, the only thing it does is basically call into the emitter. So it's really just a trivial wrapper over the emitter. But then we have another implementation, which is a closure linker backend. Closure as in the Google Closure compiler, which is a JavaScript optimizer. And here we also have a call to the emitter, but then we also call into the Closure compiler to optimize the result of what the emitter created. So we have two completely independent implementation of that trait, of that abstract class. They both comply with the contract, but they have different behaviors. Right? And since it's an abstract open class, it can also be, you can also have custom linker backends written by users in outside of the Scala.js compiler. You can write your own linker backends. And you would say, like, nobody would do that. Like, leave that to the Scala.js authors. I don't want to deal with that. But in fact, it's actually used already. There is at least one project that writes its own linker backend. It's Scala.js bundler. And it uses that because it needs to collect additional information that it's going to give to Webpack to analyze the modules that are imported from the Scala.js codebase. So it's something that we had not anticipated. It's something that actually came up in the real world outside of the Scala.js codebase. And it's possible because that abstract class is open and with a very well-defined contract. So you can implement your own, satisfy the contract, and then you can compose it again. This is another example. It's an abstraction for the JS environments, or the JS engines that we're going to use to execute the JavaScript code for run and for tests and things like that. So it has a name. It has basically a start method that takes a set of JS input files, some configuration, and returns an abstraction to manipulate the run, like to stop it and get its output and that kind of stuff. And you have one implementation of the main repo, which uses Node.js as a JavaScript engine to run and test. But then we can implement other implementations in other repositories in an independent way. So we have a JS DOM, Node.js, we have a Selenium JSenv. And then in users' builds, at least users who use SBT as a build tool, can write their own subclass of JSenv. And this is also an actual use case. Like, some people actually do that because they need to customize the JavaScript environments in very peculiar ways. But as long as they satisfy the contract of the JSenv, it's fine. So this is the polymorphism and open class hierarchies aspect of object-oriented programming. It's not as fundamental as what I said before about encapsulation, but it's still an important aspect. Okay, I can't really talk about functional programming and then not mention the M word. I sense some tension over there. So I actually wrote my own monad. Like, I didn't want it, but didn't want to, but it happens. So I have this gen method function that takes an IR method definition and returns a JavaScript tree for the code of that thing. But the problem is, while generating the method, I need, of course, to produce the resulting JavaScript AST. But for non-obvious reasons, I also need to track and record all the global variables, the JavaScript global variables from the global scope that I'm going to access from that method. And this is annoying to track everywhere. And there, I really didn't want to use a mutable builder in the middle, because I really need to be able to compose all these things like at the fine-grained level. It's difficult enough to reason about without throwing in mutable builders, even at a local state like this. So what I have is this with globals abstraction, which is a value of type JS3, and then an associated set of global variables that are accessed. And I can use flat map on this thing, and I can also use for comprehension with a for yield. So this is a map, actually. And I only wrote with globals because I wanted to be able to use flat map and for yield. But then, when I implemented it, I realized, oh gosh, I just wrote a monad. So this is it, and I was like, I want to kind of document that it's a monad, but but then maybe I should prove that it's a monad, because otherwise I'm going to be attacked by an army of cats. So I did prove it. It's in the code. I think there are like 50 lines of code, 50 lines of comments that prove that this is a monad. But yeah, the only thing it does is really like maintain and concatenate sets of strings, basically. And the only reason I wrote it is because I wanted map and flat map. But yeah, you know. Okay, that's it. I'll be happy to take questions. Thank you for your attention. So I don't see anything. So if you want to ask a question, just shout. Yeah, in the front. Is there a mic for the audience? The mic is coming.
Hi. I really like your talk.
Thanks.
I think I can argue about some things, but like there's a conversation point is a good starter.
Oh, I hope so.
Well, it's not like a question for me, but more like an addition. So when you talked about that the encapsulation is a feature of which you said it like it's an object-oriented feature per se, but like the first language with ability to define private and public parts is Modulo 2 from 1978. So like the idea, the concept itself is not a prerogative for object-oriented programming. And
I agree. I probably have said the things in a way that suggests it's specific to object orientation, and I apologize. It's not specific to object orientation. You can do encapsulation in different ways. What I would claim is that it is the fundamental property of object orientation, in the sense that if you do object orientation, the one property that is worth receiving for using object orientation is encapsulation. That does not make encapsulation that does not make object orientation the only way to get encapsulation. Does that make sense?
yeah, yes, thank you very much.
Thanks. Another question. Okay, going once, going twice. Well, then let's call it and have a break, I think.
Yeah. Thank you so much, Sebastian.
Thanks.